Okay, when we want to study general projectiles, what we have to realize is that the initial velocity takes a little bit of work to find. So here we have a cannonball, and it's launched at 50 meters per second. So that's how fast the cannonball is going. But it's launched at an angle of 36.87 degrees. So the cannonball is actually launched at an angle that looks something like this. This is the direction of the cannonball initially. Now obviously that's going to change as gravity gets to act. But here is the horizontal direction. Right here. And here is the vertical direction. And so at the instant the cannonball is launched, if it's launched at a general angle, and that's why we call these general projectiles, then the cannonball is initially moving to the right, which is horizontal, and it's moving upwards. So we're going to call this the velocity initial of the cannonball, and this is the angle at which it's launched. And what we want to do is figure out what is the component of the velocity. How fast is the cannonball moving horizontally initially? We're going to call that the velocity in the x direction initially. And how fast is the cannonball moving upwards initially? And you can see that this is going to require a little bit of trigonometry. We're going to call this the velocity in the y direction initially. Now when we launched things horizontally, that was easy. The velocity in the y direction was 0, and whatever velocity it was launched at was the velocity in the x direction. But when we launched at an angle, that's no longer true. So we've got to figure out how we're going to find these components. So a quick review of trig. The sine of the launch angle will equal the opposite side, which is the velocity in the y direction initially, divided by the hypotenuse, which is the initial velocity. And so that tells us that if we want to know what is the velocity initial in the y direction, we've got to take the initial velocity times the sine of the launch angle. And that is how we will find the velocity in the y direction initially. Likewise, if we look at cosine of theta, that equals the adjacent side, which is the initial velocity horizontally, divided by the hypotenuse, v0. Solving that tells us that if you take v0 times the cosine of the launch angle, you get the velocity in the x direction initially. So the short story is that if you want to know what is the velocity in the y direction initially, you just take the launch velocity and you multiply it by the sine of the launch angle. In this case, that is 50 meters per second times the sine of 36.87 degrees, which turns out to be 30 meters per second. Likewise, if you want to know the velocity horizontally for this projectile, you take the initial velocity and you multiply it by the cosine, because the horizontal velocity is the adjacent side of this triangle. That's why it's cosine. And that's going to equal 50 meters per second times the cosine of 36.87, and that's going to be 40 meters per second. So what we found is that when you launch a cannonball at this angle, and I know that's a bit of a goofy angle, but it's actually a 3, 4, 5 right triangle. If you launch a cannonball at this angle with a speed of 50 meters per second, then at the beginning of the problem, the cannonball is going over horizontally 40 meters per second. That's the horizontal velocity. And the vertical velocity, the velocity that is going upwards at the beginning, is 30 meters per second. Okay, so we are now going to take this cannonball and we're going to launch it and ask how long is it in the air and how far does it go. Alright, so the first thing we're going to do is set up our diagram. So the cannonball starts over here. It's fired through the air. It follows a parabolic path and it hits the ground over here. And I'm going to introduce a coordinate system for my problem. I'm going to call this point right here where it's launched the origin. And so this is the x-axis, and this is the y-axis, and the starting point is the origin. And now I need to make my variable list. So this is the standard variable list. You guys are used to it by now. So once we get our variable list, the first thing we're going to do is we are going to figure out what are the components of the velocity in the x and the y direction. And that's what we just did. So as a quick reminder, our first step, the velocity in the y direction initial is equal to the initial velocity times the sine of the angle, which was 30 meters per second, and the velocity in the x direction initial is v0 cosine of the launch angle, which was 40 meters per second. And so we can go ahead and populate those in our variable list. The velocity initial in the y direction was 30 meters per second, and in the x direction it was 40 meters per second. The ball starts here, so the initial y position is 0. The ball ends here. The final y position is 0 meters. When you guys make your variable list, please make sure you keep the units on there. The acceleration in the y direction is, of course, negative g. The x initial position is 0. It starts at x equals 0, and it ends over here at x final, which we don't know. It's actually what we're looking for. We do know the acceleration in the x direction is about is actually equal to 0 meters per second squared. And so there's our problem. Now we can actually kind of guess at the solution here. If the ball is going upwards at 30 meters per second, gravity will slow it down, and after 1 second it'll be going upwards at 20 meters per second. So after 3 seconds it'll be stopped, and after 6 seconds it'll be back on the ground. So I can roughly approximate the time this thing's going to be in the air as somewhere around 6 seconds. Now, while it's in the air for 6 seconds, it's going to go 40 meters every second. So 40 meters times 6 seconds is about 240 meters. So I'm going to guess that the range of this is somewhere close to 240, but we're going to work it out. Okay, so our step 1 was to calculate the initial velocity in the x and y direction. Step 2 is going to be to find the time that it's in the air. So we're going to solve the y problem for the time. So I'm going to solve this equation. Delta y equals the velocity in the y direction initial times the time, plus 1/2 the acceleration in the y direction times the time squared. I've got to solve that for time t. Now, this isn't quite as easy as a horizontally launched projectile, because this term right here is not 0. And because it's not 0, we're going to have to use the quadratic equation, or if you're tricky, you can solve it by factoring, in order to find t. Okay, so let me write out the equation which I'm solving. In this case, I have delta y, which is 0, equals the velocity initial in the y direction times time, so that is 30 times time, and then I have 1/2 the acceleration in the y, which is negative 4.905 t squared. And so, in order to solve this, if you want to factor out the t's and solve for t, that's good, or you can just use the quadratic equation. I'm going to factor just because that's easier, but you can always solve this with the quadratic equation. If you solved it with the quadratic equation, this, of course, is a, this, of course, is b, and it's not on here, but c would be the constant, or the term, which would be c. It's plus 0. Okay, but in this case you can actually avoid the quadratic equation. You can factor out a t, so we have 0 equals t times 30 minus 4.905 t. And so either t equals 0, that's one solution, or 30 minus 4.905 t equals 0. This is a very easy equation to solve. So if I solve this little equation, t equals 30 divided by 4.905, which is approximately 6.11 seconds. So that is how long the projectile was in the air. And that is solving the y problem. So first step was to solve the trig problem to figure out the initial velocities. The second thing was to solve the y problem for the time that it's in the air. And this was just slightly more difficult than horizontally launched because the initial velocity in the y direction was not 0, so you have a linear term in your quadratic. And then the last thing we want to do is figure out how far it goes horizontally. So I'm going to put that over here. We call this the range. I'm going to solve delta x equals the velocity in the x direction initial times the time plus 1/2 the acceleration in the x times the time squared. That, of course, is 0. So the distance it goes horizontally is just the velocity initial in the x direction times the time. And those are things we know. Slide this up here. The velocity initial in the x direction was 40 meters per second. And we know it's in the air for 6.11 seconds. So a little bit of multiplication tells us that it went 244.6 or 245 meters. And so that is what we call the range of the projectile. That's how far the cannonball went based on its initial velocity and based on its initial angle. Okay? So that is how we solve the problem for a general projectile. So the thing to remember is when it's launched at an angle, you first got to find the components of the velocity horizontally and vertically, and then you proceed solving the problem just like we have. Okay? All right, so you're going to give it a try on a couple problems.